All right, welcome back to this PChem 2 session. We're going to talk about nuclear chemistry today. I did want to remind you that there are two pre-recorded video lectures from a prior year available on the site, and I would recommend you watch those videos so that you can get the full details. Today we're going to go quickly to try and touch on as many topics as we possibly can. So you've got these two videos here, and they match up with these lecture slides that we're about to pour through. So ultimately, nuclear chemistry is a fascinating field where we have to start combining a bunch of different concepts from chemistry, from relativity, from quantum mechanics. I mean, it's an incredible mixture of fields. But if we understand nuclear chemistry, then we can really predict and understand a ton of natural phenomena, including fusion and fission in the sun or other stars, but also how to use those processes productively to make energy here on Earth. So ultimately, you know, it's a really fascinating field, and I do love to make this comment that people who study astrophysics think about elements beyond helium as metals, which us as normal chemists living in the non-relativistic world, that's, I think, humorous. But if you think about the densities of material that exist in a star, then it turns out that at these temperatures and densities, the electrons are readily removed from basically everything beyond helium. And so you've got a big old plasma floating around, which is a fun thing to think about. So there are three types of nuclear processes, I should say three broad types. Alpha decay, probably the most common one that people come into contact with in the colloquial scientific experience. These reactions involve the emission of a helium nucleus. So an alpha particle is basically helium 2+. If I strip away its 2 electrons, then I get 2 protons and 2 neutrons. And one of the common examples of that would be one of these early decays of uranium in the decay chain, which maybe we'll get to towards the end. But ultimately, this type of reaction is how we can convert from, say, uranium-238 to thorium-234 through the emission of this alpha particle. The rules are a bit different for nuclear reactions, and we're going to talk about that briefly in a slide or two. They generally don't care about the charge. We're looking really at the mass. So we're going to conserve the charge, but the mass is really what's our interesting phenomena. That changes a little bit. Many of you have read about the beta decay process. That's another broad umbrella in nuclear chemistry and nuclear physics, I should say. The basic process involves the conversion of a proton of a proton or a neutron into some other particles. So for instance, in this example, we're starting out with iodine. It's got 53 protons and 131 neutrons, and then it kicks out an electron, forms a proton. Kind of a neat process, but this is only one kind of special slice of beta decay. It turns out that this process is much more complicated than either alpha decay or gamma emission. And there's a whole suite of particles that can be emitted, things like neutrinos, which are really important for understanding advanced aspects of the standard model, which is our kind of modern theory of particle physics. So beta decay is really fascinating, but it's much more complicated than the simple picture, but we focus on the simple picture as a way to start. For gamma emission, now we're talking about ultimately a process where high energy is released as photons. And this could be a process like electron capture, where a proton inside of the nucleus reacts with an electron that's flying around close by in order to produce, basically wipe each other out. They cancel one another and emit a bunch of energy in the form of a gamma ray. So these are the three broad umbrellas for nuclear chemistry. And in the homework, I ask you to do kind of simple applications of these processes. So for beta emission, it effectively converts a neutron into a proton and electron. And To be clear, that beta particle is another name for an electron, right? The electron is a beta particle. So sometimes it's either written as E with a 0 on the top because there's no nucleons, right? The electron doesn't contain a nucleon, but it does have a negative charge, and that's why there's a -1 on the bottom. So this notation for the electron is trying to follow the same notation for the nuclei that you learned back in general chemistry. The upper number is the mass number, which refers to the total number of nucleons, and the lower number is the charge number. For protons, that's a positive value. For an electron, that's a negative value. All right, but I think with these two tables, ultimately you'll be able to write down the chemical reactions that I'm asking you to look at, following the general patterns that are presented here. So you have your last homework problem in homework 12, which will touch on these types of reactions. All right, so let's look at an example. What happens for radon, for instance, radon-226, if we undergo alpha emission? How do we solve this process? So we got to start by writing down the nuclear symbol for the element, in this case, radon-226. And since we know it undergoes alpha emission, the product side of this reaction is going to have a helium nucleus, right? 2 protons, 2 neutrons. So we end up with this alpha particle, but we're left with an unknown isotope. And in order to figure out what this isotope is, we're going to use those conservation of charge and conservation of nucleon conditions, which tell me that the total number of nucleons has to stay the same, and the total charge also has to stay the same. That doesn't say anything about the mass, though, it turns out. For most things, but in this alpha decay process, it's pretty clean cut. Sorry, for that most things, I mean things like the beta emission. It's a bit more fuzzy there. So here we've got to solve this equation for A and Z. It's pretty simple. We get 222 and 86. So in this case, we've converted radium, excuse me, I called that radon at the beginning. Ra is radium, Rn is radon. We've converted radium into radon through the emission of an alpha particle. So it's pretty straightforward, I hope. Let me check any questions on that. Throw up a reaction to make sure that you're alive today, please. It's our last Friday together, folks. What an exciting time. You're almost done with the semester. All right, great. The next topic that we can then quickly touch on is why not all isotopes are stable. In general chemistry, you learn that there are different naturally occurring isotopes for different elements, and that the average of those naturally occurring isotopes is what leads to the weight on the periodic table. But if we delve into nuclear processes a little bit farther, we can actually understand why certain isotopes are stable and some are not. So for instance, carbon-12 and 13 are both stable, but carbon-14 is radioactive and goes through some decay. If you've ever heard of carbon-14 dating, that's a process, a nuclear process, where carbon-14 transforms into other elements. The reason that carbon-14 is not as stable as 12 and 13 has to do with the ratio of protons to neutrons. For carbon-12, that ratio is exactly 1, 6 protons and 6 neutrons. And for carbon-13, it's just a little bit bigger with 1 more extra neutron. But as we get to carbon-14, where now we've increased the number of neutrons by 2 compared to carbon-12, that ratio starts to get away from this so-called belt of stability. And so on this figure on the right, it's showing you where the stable elements lie. And you can see that this 1-to-1 ratio, it doesn't hold for that 1-to-1 ratio, except all the way down here at the very bottom. And even if we zoom in for carbon, you can see that it is above this 1-to-1 ratio line. So as we start to get away from this kind of belt of stability, then the elements decay to try to get back down to the most stable isotopes. The reasons why they decay are ultimately related to this shell model. And for those of you who remember reading about Maria Goeppert-Meyer, she was one of the pioneers of understanding this phenomena. Let's just quickly take a look at what we mean here. If you look at this diagram, it's actually showing you the different shells with on the right and without spin orbit coupling. And this was one of Maria's major contributions. By incorporating spin orbit coupling, Goeppert-Meyer was able to show that certain numbers of nucleons, these so-called magic numbers, fill shells, which very much reminds us of the electronic structure problem. So think back to general chemistry when you were learning about the octet rule and noble gas atoms. In this case, those magic numbers are 2, 10, and 18, right? The number of electrons needed to fill these valence or total shells. We have the same idea for the nucleons. And when I say that, I do mean both protons and neutrons together. So ultimately, by looking at the shell model, we can understand why certain isotopes are not stable or stable based on the shell filling, just like we would think about the octet rule for general chemistry in thinking about the stability of atoms. So there's a pretty good similarity or analogy between the nuclear shell model and the electronic shell model. All right, I've talked about the magic numbers. I do want to briefly mention that ultimately there's this force keeping the nuclei together called the strong force. As chemists, we don't normally come into contact with anything outside of the electromagnetic force or gravity, right? We're worried about masses, and then we're worried about charges. But if we think about what's going on inside the nucleus, it turns out that the only reason the nuclei stays together is because of this strong nuclear force. So if you want to read more about one of these other 4 fundamental forces in nature, I've also included this little link here for you. But it is a fascinating force that kind of binds the nucleus together. Keep in mind, protons all have the same charge. So somehow there's a force strong enough to contain, 70 protons all stacked up together. So indeed, the strong force is extremely strong when we think about it on a very short length scale. All right, I think that's all I want to say about this slide. I did mention that decay processes tend to move you towards the belt of stability, which is important because, again, that's where all of those long-lived isotopes lie. If we do have isotopes that undergo decay, they may undergo several decay processes before they reach the belt of stability. And so one of the best examples that we can use to understand this process is the decay chain of uranium-238. And this process is important to understand because uranium is used in a number of applications, both for energy and the military. In this case, if we start out with uranium-238, it can undergo certain decay. And if you look at this diagram, each blue arrow represents an alpha decay. So we've actually already seen on that very first intro of alpha decay that uranium-238 will decompose into a thorium-234. That thorium nucleus, or I should say isotope, excuse me, is itself not stable. And so it will go through some beta emissions, some beta decays, in order to get to a new isotope. In this case, that thorium will undergo 2 beta decays in order to get to the uranium-234. And then if we follow the rest of the diagram, you can see that there are many more processes before we finally reach lead-206, a stable, long-lived isotope. But what's fascinating about this whole process is that we can actually apply the same fundamental concepts you learned in general chemistry to think about the nuclear reaction. So in general chemistry, you learned about Hess's law, which told me I could break up a chemical process into a series of steps and then compute the total enthalpy or Gibbs free energy change as a sum of those processes. Well, it turns out in nuclear chemistry, we can do exactly the same thing. So if we start with uranium-238 and we write down all of the individual reactions that lead us to lead-206, well, we can finally add them all up together to get one final conclusive reaction that we could use to then calculate the nuclear reaction energy. So if you're taking a stab at the extra credit problem, if you use that concept from general chemistry, it might make your life a little bit easier, more straightforward anyway. I do want to touch on that last bullet point here, though, that each step is accompanied by a change in mass and therefore also a change in energy. We don't necessarily conserve mass in these nuclear processes. And in relativity, mass and energy can be interchanged. So ultimately in this process where we go from uranium-238 to lead-206, not only will there be a change in the element identity, but we may also end up with changes in mass that lead to the energy being released. Whew, got about 5 minutes left. And like I said, I'm just kind of like blasting through this. I encourage you to go back and check out those two more focused video lectures to get the details down. So let's take a second now and talk about the reactions more in depth, what's conserved here, and how we calculate the reaction energies for these processes. Over here on our chemical reactions from GenChem, the total mass that we started with was equal to the total mass that we ended with. And we also conserved charge. So whatever charge we started with on the left, that's how much charge we had on the right. And that was the premise of like everything you've ever done in general chemistry up till now. But in nuclear reactions, we have to give that conservation of mass up. We no longer can conserve mass. Instead, we're conserving the number of nucleons. And this number of nucleons is like, counting the number of particles. So as we've looked at this reaction before, we have that the mass on the left is not necessarily equal to the mass on the right. And you can do this if you just run and look up some accurate masses for these things. You'll see that they don't add up. The reason that they don't add up, we don't have time to discuss, but it has to do with this thing called the nuclear binding energy. And as I mentioned a moment ago, that's related to the strong force. I learned a neat fact while trying to brush up this morning, but it turns out that the mass of a proton is really mostly due to this binding energy for the particles that make it up, which I think is pretty neat. We have this kind of equivalence between mass and energy. So where does that come from? It comes from our friend Einstein in the theory of special relativity. Special relativity tells us that the energy, the rest energy E, is equal to the rest mass m times c, the speed of light, squared. So for these nuclear processes, we're applying this equation, E equals mc squared. And we can calculate the m by looking at the mass difference of the reactants and products. So in previous reactions, you've always thought of m as a fixed thing, right? It's conserved on the left and right. But now we have to calculate the change in mass for this reaction. So to do that, for instance, if I'm looking at this uranium to thorium production, I can calculate the mass of thorium, again, for 1 mole. Keep in mind that we are still using like molar coefficients. These numbers are belonging to the element symbols, but there's kind of a 1 for 1 mole standing in front. So we can get the masses from, say, the molar masses. So 1 mole of thorium weighs 233 and change, about 234 grams. We add that to the mass of helium, right? Products minus reactants. Isn't it amazing we can apply these identical concepts from general chemistry on this very advanced concept of special relativity? I personally find that very fascinating. But it all comes down to this state function idea. In the end, we get a delta M, right? A change in mass that's negative. Take a second and really digest that, right? In this reaction, mass is lost. Uranium weighs more than the 2 products on the right. But as a result, that mass difference is converted into an energy. So it's not that there's such a thing as negative mass. It just means that the mass difference has gone from a heavy state to a lighter state. And where does it go? Well, it goes into energy. So we can take this delta M and plug it right into the equation, accounting for units. And so let me say that it's important to work in SI units here. We've got to convert our grams to kilograms so that we have joules at the end of this. But from this small calculation, what have we discovered? All right, we started out with 1 mole of thorium, 1 mole of uranium producing 1 mole of thorium and 1 mole of helium nuclei, alpha particles. The mass difference is 4.6 milligrams for that 1 mole, right? Negative. Come down here, plug it in. Because we have to square the value of the speed of light, we end up with this gigantic release in energy, right? Think about this number. This is 410 billion joules, much larger than any ordinary chemical reaction. Let me see your reactions. Think about this number compared to what we normally talk about, right? This is 410 times 10 to the 9 joules. Normally we deal with, things much, much smaller than this. But fortunately, for the most part, it's hard to get 1 mole of this stuff to decay simultaneously. You've got to have a bunch of tech for that. So for the most part, if you discover a sample of uranium, you'll be totally fine, right? Because we're not seeing 1 mole of this decay simultaneously. It's normally a slow process. All right, I think we are more or less out of time. There are these examples here, which I'll draw your attention to for the homework. If you want to work through them, you've got those 2 other video lectures that will help you do that. But yeah, I think otherwise, there's also some points about fission if you're interested in that. So I'd encourage you to walk through those videos again and just see what I had to say. I'm going to stop recording. I'd be happy to answer any questions, but I think that'll be it.